Good morning, everyone. Looks like we're having some people still trickling in, so I'll give that a few seconds. All right, I think we might be there. Good morning, everyone. I'm Phil Chang. I'm the president of the SRS Foundation, and I'm so pleased and excited that we are able to host this new series of educational webinars. So today, researchers will learn the science behind a sleep product and how it works directly from industry scientists with a question and answer opportunity at the end. So let us explore how our shared mission of growing knowledge can help further the field. And please note that the SRS and the SRS Foundation do not explicitly endorse any products discussed on today's webinar. So we are especially excited today because we'll be learning about the science behind the Nox BodySleep 2.0, Achieving Conclusive Home Sleep Tests, presented by Nox Medical. So now, without further ado, I'd like to introduce and turn over the webinar to Doctors Jan Augustin and Heidi Riney.
Thank you very much, Philip. And thank you to the SRS Foundation for hosting the webinar. And thank you all for joining. We heard that there's a record number of people joining today. So today I'll be talking about an AI-enabled medical device that we developed at Nox Medical. It's called DeepRESP, and where Nox BodySleep 2.0 is one of the foundational AI models in the product. We're also so great to have Dr. Heidi Riney with us, who is our Chief Medical Officer, and she will be talking about the clinical implementation and the impact the product has had in our own clinical operation. The key idea is to talk about the Nox BodySleep and how it influences the quality of and the results we get from home sleep apnea testing, and converting them into conclusive testing with results which are much closer to what you would expect from a PSG, but without adding the burden of EEG to the patients. We'll talk about the approach we took to develop the model, the philosophy behind developing AI medical devices that we're approaching, and how we are kind of raising the bar in both the quality and the transparency of the validation that we're doing of the AI medical device. So before I talk about the medical device, I just want to talk a little bit about Nox. So Nox Health is a global sleep health company which works across a continuum. At Nox Medical, we develop the medical devices. So these are all the sensors, the recorders, the Nox A1 and the Nox T3 recorders, all the software, like the Nox Tunnel software. We recently had cloud-enabled products, including the DeepRESP AI medical device. But at Nox Health, we also operate a regular sleep clinic and the value-based sleep care management program, where really our goal is to have patients being successful on their treatments. And then we also offer digital therapeutics for insomnia. And this puts us at a very unique position when we're developing medical devices, because not only do we have the expertise and the engineering expertise to develop the hardware, the electronics, or the signal processing and everything that influences the data that we collect, and of course the AI that's analyzing the data, but we also have in-house the expertise of the sleep techs who are conducting the sleep studies, collecting the data and scoring it, the sleep physicians who are interpreting the sleep studies and taking care of their patients, and then we are monitoring the success of our patients on treatment. So really what motivates us in developing the medical devices is to have patients who are successful on treatment. AI is not new to Nox. Already in 2016, we introduced the first AI models into our Nox Tunnel software. So these were deep artificial neural networks, similar to what we are using today, and we were using them to score sleep stages from EEG data. Since then, we've introduced 4 other AI models into the Nox Tunnel software, scoring sleep stages and arousals from EEGs. And then we have the Nox BodySleep version 1, which scores sleep stages from the respiratory inductance plethysmography, or the RIP signals, collected in HSAT studies. Now I'm going to talk about DeepRESP. 2025 was a very big year for us at Nox Medical, because we had not only 1, but 2 clearances from the FDA on the cloud-based AI medical device that we call DeepRESP. So we had version 1 cleared earlier this spring, and just about 2 weeks ago, we got the second clearance for DeepRESP version 2, which is really adding capabilities to the DeepRESP medical device and helping us to grow that device. So DeepRESP is an AI medical device that's used to autoscore PSG and HSAT studies. And today I'm going to be talking about the HSAT scoring and particularly focusing on the role of the BodySleep 2.0 AI model, which is one of several AI models in the DeepRESP product. What really motivated us is that conventional HSAT is not conclusive. And what that means for us is that the REI that comes from an HSAT sleep study is underestimating the severity of sleep apnea because it does not take into consideration the hypopneas that end in arousals, and it does not take into consideration the sleep time. Whereas the AHI that you would typically get from a PSG counts all the apneas, all the hypopneas, regardless if they end in desaturations or arousals, and of course records the sleep time. We see that many HSAT devices are relying on oximetry as one of the fundamental signals, but the FDA has voiced concerns about the accuracy of oximetry for patients with dark skin, and there is preliminary data indicating that desaturations may be underestimated in people with dark skin. Oximetry can also be affected by comorbidities and medications, and this is one of the things that we also wanted to address. Women, younger patients, and non-obese patients are more likely to present with sleep apnea with hypopneas that end in arousals than desaturations. So these are patient groups that are typically underdiagnosed in conventional HSAT studies. And what really motivated us to develop the BodySleep 2.0 AI model was to add the capability of scoring sleep and arousals in HSAT without increasing the burden of the patients. And the way it works and the workflow is that HSAT sleep study is conducted and the data is uploaded to our cloud, where we run the auto-scoring. And this includes the Nox BodySleep 2.0, which scores the sleep stages and arousals from the wake signals. And of course, we have AI models to score the respiratory events, so apneas, hypopneas, desaturations, and such. After auto-scoring, the raw data is available for manual review. And since the raw data is familiar to sleep text, I mean, the data we're collecting are the RIF signals, the SpO2 signals, the cannula flow signals, and all these signals that sleep texts are used to looking at in HSAT studies. And the events that we're outputting are also familiar to the sleep text. So these are the respiratory events, the sleep stages, the arousals. There's nothing which should be alien or unfamiliar when reviewing the data and making sure that the scoring is correct. After manual review, the sleep study is ready for interpretation by a physician, where they have access to all the standard parameters like the AHI, the ODI, the arousal index, and we also added ventilatory burden, hypoxic burden, and the endotypes of sleep apnea. So here's an example of the output from the Nox BodySleep algorithm. So what we use as inputs to the AI model is just the signals from the Nox biosensors. The Nox biosensors track the breathing movements of the chest and the abdomen, and this is what we feed into the algorithm. We output sleep stages, wake, REM, and non-REM, and what we added significantly, is like the significant addition in the Nox BodySleep version 2 is the ability of scoring arousals, which was not present in version 1. And here we just see an example of a hypnogram from a manually scored PSG sleep recording. At the top, we see the wake periods are in yellow, the blue areas are the REM periods, and then the non-REM periods, and then the red are the REM periods. In the middle panel, we have the same sleep recording scored with the BodySleep. We see, of course, there's high concordance between the scoring, where we have the yellow representing wake. Now all the non-REM sleep stages are collapsed into non-REM, which is green, and then we have red, the REM stages. And the bottom panel shows the hypnodensity plot, which is giving us a little bit insight into the AI model, because the hypnodensity plot is the probabilities outputted by the AI model for each sleep stage in each epoch. What really gives us confidence in the BodySleep AI model is that it's founded in physiology. We know that breathing patterns are very different between wake, REM, and non-REM periods. During wake and REM, breathing tends to be irregular. However, during wake, breathing is controlled automatically and voluntarily, and typically the upper airway is open. During REM periods, there is muscle atonia in the intercostal muscles of the rib cage, meaning that the diaphragm does most of the heavy lifting in breathing during REM periods. And we see this in the difference in the contribution of the thoracic and abdomen belts. Also during REM periods, typically the upper airway starts to narrow or become collapsed. So you see flattening and respiratory events occurring. During non-REM periods, breathing tends to be irregular, respiratory rate tends to be a little bit lower, and the contribution of the thorax and the abdomen is more equal. Also, there is a narrowing of the upper airway that can lead to flow limitations and respiratory events. So when we were demoing BodySleep version 1 to our internal physicians, one of them noted that if we had the ability to score arousals, this would be very impactful for diagnosing sleep apnea, because this would allow physicians and sleep techs to score hypopneas that end in arousals. And at this time, we were not sure that this was even possible. But we started just training an AI model and seeing what would come out of it. And when it worked, and it started to actually score arousals, we were amazed, because we didn't really understand that this information was in the data that we were collecting. So this drove us to look into the literature. And of course, in the late 90s, early 2000s, people were making studies where they were inducing arousals using acoustic stimulation, and they saw a respiratory response to an arousal. So there was physiology there that was backing this up that we were just not aware of at the time. Here I'm just going to show you an example of how the signals look during arousals. So here we have a segment of a sleep study from a patient with periodic limb movement, and you see in the lower two traces the EMGs of the right and left leg, and you see the periodic bursts of the limb twitches. In the top two traces, we see the thoracic and abdomen rip signals, and when the twitches are occurring in the limbs, you see how there's a kink in the thoracic rip signal and how the amplitude of the abdomen signal increases. I'm not saying that these are exactly the features that the AI model is picking up to score the arousals, but it just goes to show that even us, we see that the rip signals are influenced in these periods where the arousal occurs. Now about the AI model. Nox BodySleep 2.0 is a deep artificial neural network. When we train it, we use a methodology called supervised learning, where we use the manually scored sleep stages and arousals from PST sleep recordings as the references, and we feed into the model the RIP signals. So the model never sees any EEG signals. It just sees the scoring and the RIP signals, and we train the model to use the RIP signals as inputs and output the sleep stages and arousals. Once we have a model that's performing to our liking, we stop the training, and there is no mechanism for the model to changing or evolving or continue learning once we stop the training. With the frozen model, we conduct a clinical validation, and this is what we use for the FDA application. And any changes to the model need to go through a new FDA application. So we, of course, make sure that the model is not changing over time, because this would trigger us to do a new FDA application. Here is just a figure from a paper that we recently published on the Nox BodySleep 2.0, showing the input signals in panel A at the top. And we see the abdomen in blue and the chest in orange. Then in panel B, we have the arousal probability signal, which is one of the signals we output from the model. And in panel C, we see the probabilistic output of the AI model for each of the three sleep stages. And what we see in the beginning, in the first 2-3 epochs, is that REM seems to be the most probable sleep stage. And if you look at the top panel on the RIP signals, we see that this is where the abdomen is really dominating the breathing. And in the later epochs, the contribution is more equal between the abdomen and chest. And this is where the model starts to predict more non-REM sleep stages. The arousal probability we output for every second of the sleep study, and if the arousal probability crosses a threshold for a certain amount of time, we score the arousal event. The clinical validation of the medical device is really what separates medical devices from other AI devices. And we are aware that there is a concern in the community that AI medical devices can have significant impact on patient outcomes, and many of the AI medical devices may not be validated sufficiently to really prove the performance of them in the clinical practice. And in taking on this concern, we really want to lead by example. So when we were setting up the validation for the DeepRESP medical device, we decided to really raise the bar in both the amount of data that we're using for the validation and in the amount of information that we're sharing about the performance of the device and how it performs. So the data that we collected, we made sure that it was representative of the data that the device will be used on in the real world, that it comes from patient populations that will be used, device will be used on. We made sure that the data was standard clinical data and anchoring it to the best clinical reference methods. And I just want to give a little bit of context here. What I did is that I looked at FDA-cleared medical devices that are used in sleep diagnostics that were cleared in the period from 2020 to 2024. So these are fairly recent clearances by the FDA. And of the 13 medical devices that I found these publicly available summaries from, 13 were using 300 or fewer sleep recordings to validate the performance of the devices. Some of the cleared devices don't disclose how many studies were used for the validation. So of course I did not include them in this graph. And what I actually found was that most of these devices were using fewer than 150 sleep recordings for the validation. And why does this matter? I mean, it matters because, in my mind, when we talk about these validations, more is more. More data is better. More transparency is better. Because sleep apnea is a heterogeneous disease. It affects the patient groups and it presents differently in different patient groups, like men and women, young and old, people with comorbidities or medications. We also know that sensors perform differently across different patient populations. So we mentioned the oximeters with how they are impacted by skin tone, comorbidities, or medications. Of course, there are different disease severities, and with small validation cohorts, it's very unlikely that the validation results represent the performance in key patient groups and that they have statistical power to support the performance in all of these patient groups. So what we did, raising the bar, was that for DeepRESP version 1, we used almost 3,500 sleep recordings in the validation. For DeepRESP version 2, we raised the bar even higher, using almost 5,800 sleep recordings for the validation. This is approximately 40 times more what most other devices have been used for most other devices. The data we collect comes from multiple centers across the United States, from standard clinical practice, allowing us to do robust subgroup analysis. And I'm not going to I don't have time to go into all the details here, but we are planning to publish the methods and the results in scientific papers to allow anyone to look at this and make up their mind if they agree with the methods and understand really the results. The data we collected, we made sure was representative of the data that the AI medical device will see in the real world. We collected sleep study data from PSTs, type 1 and type 2, from adults. The reason we use PSTs is because we need to have the scoring of sleep stages and arousals and the hypopneas that end in arousals. Type 1 PSTs are very important to us because these are people who do type 1 PSTs are typically patients that were not diagnosed with sleep apnea in their home sleep apnea test. So they are typically represent people who are difficult to diagnose with HSAT studies. But they also include patients that have other sleep disorders like periodic limb movements or bruxism or something else. Type 2 sleep PSTs were also very important because in our case, these sleep studies were conducted in the patient's home and the patients were administering the sensors on themselves. So this introduces all the different variables that you may experience in home sleep apnea testing when it's recorded in the home and patients are putting on the sensors themselves. We used standard clinical scoring, so the data was collected by ASM certified sleep labs, reviewed and scored by sleep technicians and interpreted by board certified sleep physicians. We were not using multiply scored sleep recordings to create the consensus scoring, because we know that there is interscoring variability out in the real world, and we wanted this to be reflected in our validation data. When we create multiply scored sleep recordings and we make a consensus, we're actually reducing the noise in the scoring, and then this may result in validation results which are overly optimistic and may not translate very well to how the device performs out in the real world. The data that we use to train and validate the model are clearly separate. So when we're collecting training data, we collect adult sleep recordings from around the world. So we collect data from North America, Europe, Asia, and Australia. And the reason we do this is that, of course, we want to include a very diverse patient population, but we also want to include the variability that you would expect to see in clinical practices or even environmental factors that may impact the signals that we collect and may impact the performance of the AI device. We collect clinical data and research data because our goal is really to have as much variability in the training data as possible. You can think of it like the model should have seen it all when we've done the training. The validation data, however, is entirely independent of the training data. This means that we use data that originate from sleep clinics that were not represented in the data collection for the training data. So we really separate it on the sleep clinic level, and we do this to try to minimize any information in the training data leaking into the validation data. So we try to have different sleep tags, physician and patients. So we are not learning the validation data during training, and there's a very clear separation between these two things. And now we have some data to show you. So what I'm showing here on the scatter plot are the manual, the AHI values from the manual scoring of the PhD studies that we used for the validation. On the x-axis. On the y-axis, we have the REI values. And I created these REI values by excluding hypopneas that end only in arousals and using the recording time as the denominator. And I'm using REI 3%, so I'm including the 3% desaturations. So it should be really just looking at the impact of these two things, the hypopneas that end in arousals and the sleep time. And what is not surprising is that the REI underestimates the AHI. I think this should be not news to anyone. I draw these red dashed lines to indicate AHI and REI of 15. I could have put it at 5, I just put it at 15 because it's kind of easier to see, but the message is still the same. In the lower left corner, we have all the patients that have an AHI below 15 and an REI below 15. So in this classification, these would be the true negatives. In the upper right corner, we have the patients that have an AHI above 15 and an REI above 15, and these would be the true positives. The patients that are most interesting to us are the patients in the lower right corner. So these are patients that have an AHI above 15, but an REI below 15, and these are the false negatives. So in the table, I'm showing the same data. And I just want to draw your attention maybe to the first line in the table to explain a little bit what it's telling us. So in the first line, we have the REI values between 0 and 5. And in the columns, we have the corresponding AHI values for the patients that had an REI below 5. And we see that 159 patients had an REI below 5 and an AHI below 5. These are the true negatives. But what is more interesting is that of those papers that had an REI below 5, 994 had an AHI between 5 and 15. And even 642 had an AHI between 15 and 30, and whopping 177 an AHI above 30, and they had an REI below 5. So now I'm going to show you the AHI that gets if we process the same sleep recordings with DeepRESP as HSAT studies. And now we get these orange points. So we see right away that the orange points, they track the line of unity much better than the blue points. And now if you look at the top line on the table, so these are patients that had an AHI from DeepRESP between 0 and 5. And we look at the columns again, there are 110 that had an AHI between 0 and 5. In the REI case, when they had an AHI between 5 and 15, we had 994 that had an RAI below 5. In the DeepRESP case, only 1/3 of those patients is still classified as having an AHI between 5 and 15. For the AHI group 15 to 30, we had 642 with an RAI below 5. We have only about 10% of those patients with an AHI from DeepRESP, which is below 5. And for the group 30 plus, in the RAI case, we had 177 with an RAI below 5. And in the DeepRESP case, we had about 5% of those patients with an AHI above 30. So it shows that the AHI we get from DeepRESP is much closer to the AHI from a PhD than you would get in a traditional PhD study, HSAT study. Here I'm just going to show you a little bit the sensitivities, specificities, and accuracies for these common AHI cutoff values and the AHI above 5 from our FDA validation. And this is a configuration that we used in the FDA application, which we call HSAT flow, where we include the abdomen and thoracic rib signals. We have the SpO2 signal, and we have the nasal cannula signal to measure flow. But we also had a different variant, which we call HSAT rib. And here we only measure the rib signals and the SpO2, and we don't have the nasal cannula. And what this shows us is that the performance is still very high when we exclude the nasal cannula, and tells us that even if you have a HSAT study where the cannula signal is not reliable, you can still have a successful study, and it's still useful. So what I've shown you here today is that DeepRESP was validated on the largest data set used in a 510(k) submission with the FDA, about 40 times larger than our competitors. The performance was validated, included important patient subpopulations, and in our validation data that we hope to submit in our paper, we can break this down into all the different subgroups. We did show significant improvements in sensitivity and specificity over conventional HSAT. And what really makes us believe in what we're doing is that everything we are doing is based in known physiology. And the input signals are familiar to sleep techs and physicians, and this output scoring is also familiar. So it's easy to review and make a correction and make sure that the output of the sleep study is correct. So now I'm going to hand it over to Dr. Heidi Raimi, and she can tell us about how we implemented this in our own clinical practice and the impact it had for our patients. Thank you.
Thank you very much, Yon, and thank you, Dr. Chang. Thank you, SRS Foundation, and thank you to everybody who's joining us today. So, really kind of I'm going to double down a little bit on what Yon had talked about. So really want to focus on what it means to have conclusive sleep testing, what we feel defines conclusive sleep testing, and then definitely talk about what that clinical impact has been since we've been able to institute it in our programs. I think I want to kind of go a little bit of a history lesson beforehand to kind of understand what really drove us to want to get to this point. What was really the driving force in Yon and his team trying to get to conclusive home testing. And so I think it's where home testing was designed in the first place. So home testing, really when the ASM came out with their kind of, what they would say as far as when it should be use case, there was a lot of hesitation in doing it. So it happened in 2007, but there were a lot of discussions beforehand. And I think the fear was that they had that if people went and had home testing, that there may be a challenge where people would be missed or underestimated in their severity, and we might create a gap in care. And really the intention was never to replace the gold standard PSG and diagnose a full spectrum of sleep disordered breathing. It was really designed for uncomplicated adults with a high pretest probability of having moderate to severe sleep apnea. And there were reasons for it. I think we were definitely understanding that the impact untreated sleep apnea had on cardiovascular health, and diabetes, metabolic health, neurocognitive disorders. And we knew there were a lot of people that we couldn't get to. And there was a supply demand issue. There weren't enough sleep physicians or labs in order to care for all of those patients. So really a lot of it was, well, how do we get to those that we know likely have the disease? And I will say that I started practicing sleep around the time that this came out. And in our lab, it was really a smaller minority that were having those tests. And I would say where we are now, we have seen that pendulum has swung the other way, where payers really kind of routed patients irrespective of what their symptoms were, irrespective of their comorbidities, really what they were coming in for. And really, if they were able to have a home test, that was the first line. And I think that even got more so around the pandemic, where a lot of sleep labs closed. And so we were having to rely on home testing even more, and some of those labs were not able to reopen. But unfortunately, what happened by sending everyone there, it's kind of as Joan talked about, a test that was built really for a narrow population was now meant to diagnose everybody. And so you're talking about women, younger population, non-obese patients, individuals who have darker skin tones where maybe the devices may not be able to pick it up as much. Also, people have comorbidities, maybe on medications that again may impact the results of the test. And so, what unfortunately happened is kind of what the American Academy of Sleep Medicine was a little bit nervous to begin with, which is that it created an environment of false negatives, inconclusive results, underestimation, and in some cases, overestimation of disease severity, which had the inadvertent consequence of widening care gaps. And so I kind of think about this a lot. So where we are again with all these different devices and different ways that we can diagnose sleep apnea, and I'm going to put my neurology hat on for a second. And I think about it that if we approach epilepsy in the way that we currently approach sleep apnea diagnosis in the home, if we imagine our diagnostic test simply told someone yes or no, do you have epilepsy, without giving any information about the type of epilepsy classification, what the etiology is, what treatments may be beneficial, what treatments may actually make the disease worse. And imagine on top of that, if that test didn't work for every population who had it. It was good for some, but not great for others. I would say that that would be really hard to accept, right? We wouldn't consider that acceptable. It wouldn't be clinically responsible, and it wouldn't lead to good outcomes. And so I would say when we diagnose epilepsy conclusively, right, when we can get that, it's important because the consequences of misclassifications are huge. And the same goes for sleep apnea. It's no different. Sleep apnea, as Dr. Gustafson said, is not a binary condition. It's not just yes or no, do I have it? It's a heterogeneous disorder that has multiple physiologic drivers that can impact treatment predictions and outcomes. And so having a simple yes or no test on the diagnostic end is not enough for a disorder, which is complex, especially now that most patients are being diagnosed at home. So I think, the idea of having inconclusive studies disproportionately affect different demographics, one of which we're going to focus on today, which are women that may send patients down the wrong treatment path, or more often, unfortunately, no treatment at all, is it has massive consequences. When we misclassify sleep apnea, it impacts cardiovascular health, metabolic health, cognition, mood, daytime performance, safety, pretty much everything that you can think of. So when we think about, what conclusive tests mean to us, it's really encompassing that all diagnostic testing really needs to close that gap in care that has really been created by conventional home testing. So the idea is to deliver accurate, equitable, and actionable diagnostic information for every population we see, irrespective of demographics and comorbidities. And it must deliver actionable physiologic information, not just a yes or no answer. We really want to eliminate those false negatives and quantify the severity of disease and have the ability to map underlying physiologic traits that may help us inform on what treatments may be most successful for a patient. And that's what we would define as conclusive sleep testing for us. And again, as we talk about sleep apnea, the why that matters, it's a chronic systemic disease with wide-ranging consequences that, when again left untreated, can really increase healthcare utilization, healthcare costs, and morbidity for patients. And we know in the current environment, a lot of patients don't get tested or diagnosed, but also even when they do, a lot of them fall off of treatment. So if we have the ability to be able to provide those insights to patients, we really make a big difference in, again, improving outcomes for all. So over here, a little bit as kind of what Dr. Gustafson showed. Over here is we're looking at the signals that we typically would get on the type 1 recording or a PSG. So on top are the signals, the direct signal inputs that we get. And then on the bottom are the outputs we get, what we're able to score with those signals. In the middle, we see what we get with a typical type 3 recording. So as you can see, it does not usually include EEG, EOG, or chin EMG. And with it, we often miss, again, those arousal events that Dr. Gustafson was talking about. So we can't get those hypopneas associated with arousals that can, again, reduce or underestimate disease severity, as well as we don't get sleep time, which also can impact the ability to estimate someone's severity. With the deep machine learning using the RIP belts, we are able to close that gap and be able to now get that arousal data as well as sleep time and sleep stages so that we can really get a full diagnosis for a patient and again also address underlying physiologic drivers because we are looking at direct respiratory signals. And so this study, so as you know, I think Dr. Gustafson was showing earlier, I remember sending him a lot of screenshots when we'd read a study. And you can see in here, this is an example of someone who's had a type 3 study without the use of AI. And when you're looking at the flow signals here, and I don't, I'm actually, I'll go back here. I wish I could show you with my cursor here, but you can see the flow limitation in the nasal cannula, in the RIP belts. And so you can see also the notching that you talk about in the belts, and you see a hyperpnea response. And it's something that if you look at it, you would want to be able to call, but it doesn't have the associated desaturations that you need to do it with a home test. But this is someone that you see likely has disease, but you're unable to estimate it. And so when we're able to add Nox AI in the same patient, up here in the green boxes, you see RA. That's the respiratory arousal that the AI is able to pick up. So now we are able to count that flow limitation hypopneas we were able to see. It also did a great job of picking the obstructive apnea event that we missed when we were manually interpreting the study. So it's able to capture all of those events. And again, it's looking at the thousands of studies to be able to map it. But it is something that, as he said, it's not a black box. You can visually see the flow limitation and you can see the response with that recovery breath after the event. So when you look at the numbers, if you look on the top, if we were looking at what that study would have looked like without AI, we would have had just recorded hours and not sleep time. So we would know that they had about 10 and a half hours in bed, and their REI would have been 4 events an hour. So technically, it would have been an inconclusive study, which often, unfortunately, people will actually say is a negative study. So they might think, I'm okay, and that's it. On the bottom, when you are able to add AI, we now have a sleep time, and we're able to, again, to get non-REM, REM, and wake time, but now we know it's 9 hours. And again, changing that time, you're able to actually, sometimes you underestimate apnea severity if you have long recording time because you're not 100% sure if they're in bed or asleep. And we see there that the AHI now is 11.8 events an hour. We also have an arousal index, so we can see that there's disruptions beyond the respiratory events that we're seeing there. And so this is someone now that we would be able to treat with this and not have to see the drop off that we often get when someone has an inconclusive study. So now I want to go in and I'm going to summarize these numbers a little bit, but these numbers are really exciting for us. So we were able to integrate Nox AI into our clinical programs in May of this year. And we have 2 clinical programs. One is our brick and mortar clinic in the Atlanta area. So we have a full service in, a laboratory as well as our home testing. And we also have a nationwide value-based sleep care program, which is really more of an employer program. And so when we combined the number of patients who had tests through using Nox AI, it was nearly 3,100 patients. And this was for all, and then we're going to break it down a little bit based on gender. But what you can see here is when we look at the different thresholds, and really if you look at the diagonal where it's bolded, that's where you see agreement. But the big issue that we see is that kind of as you go from left to right, we see all of the things that essentially would have been missed if we did not have AI. When you look at the total number of patients that would have been told they had an inconclusive study, I'm going to put it as a patient number, which is 351 patients would have been told that. In reality, only 37 of them were truly negative. So that's over 300 patients that we likely would have missed, who likely would not have started treatment, which is a huge deal. And if you put it on a population level, we can talk about what the impact of that is. You also see a misclassification of mild, where more patients that were called mild actually in reality were more in the moderate to severe range. And again, we'll go through those numbers in a couple of slides. The other big one, so I think we knew, and I will say I was a little shocked by this, that there is a discrepancy or a gender gap in what we would see with men and women with home testing, right? Because physiologically, women tend to have shorter duration hypopnea events. Their airway doesn't tend to be as collapsible. And their events tend to end with an arousal as opposed to an oxygen desaturation that would be clinically significant to be seen on a home study. And often, these tests may underestimate severity or again, miss it. And we saw that when we looked here. So we had, if you look on the top, when we look at the male versus female, so we had 1,785 men and 1,147 women. And the big thing that gets to me, and we'll go through the percentages, that women were more than 2 times more likely to have an inconclusive study versus men. That number was nearly 18% versus about 7% in men. Those numbers are dramatic when I think about it. And then on top of it, when you actually look at true negatives, it's 2% is a true negative in women versus less than 1% in men. So being able, with the addition of AI, to reduce that gap in care in the diagnostics and getting to the diagnosis is huge. So let's go through what these numbers are. So again, we've had over 3,000 patients. Without AI, we would have had 11% would have been inconclusive, where only 1.2% were truly negative, and that's about a 10% percentage gap. For mild, we also found that 35% initially would have been called mild without AI, but with it, it went down to 22%. So that number dropped by 13%, but we saw an increase in our moderate to severes by 24% with the use of AI. And I would say, I think the number's over 50% in general that upgraded their classification on levels of severity with the use of AI. And so, again, what does it mean getting that test right the first time? It minimizes patient drop-off since many don't come in for that. So just anecdotally, when we talk about those numbers, when we looked at about 2.5 years of data in our clinic where we do have a lab, and this is somewhere where we will let patients know before they have a home test, hey, it may be inconclusive. We may need to have to do a second test so they're aware of it. We call after. Our inconclusive rate was somewhere between 14 to 15% in that 2.5 year span, but we only were able to get 35% of those patients to come in for another study. So we lost 65%. And in the literature, that number is probably closer to 25%. If that, I think actually that's probably even generous. You tend to lose a lot of people. The other thing we tend to see is when people often have to get that second test, they're essentially, when you look at adoption to therapy, they're more likely to adopt therapy if you get it right the first time. But when they get the second diagnosis, there are questions between the two tests, and you see that people are less likely to want to pursue it. So again, getting it right has real ramifications in what we see. And I'm going to throw another slide to kind of even bring that point home more so. So we did want to look at that. So, and we'll also add that there is a lot to this that may impact these numbers, but just at a glance, we were curious, does your severity make an impact on your adoption to treatment? So we looked at 2,500 of our patients, and this is in our telehealth program where CPAP is their option for therapy if they are diagnosed with sleep apnea. And just for definition's sake, adoption is if they initiate treatment and use it for more than an hour a night just to make sure they're not just trying to get used to the device. Adherence is, are they still using it a year later? Persistence to therapy is, are they still using it 2 years and beyond? And what got us, and I would say the literature has not really always supported that severity always goes along with adoption and adherence to therapy. But we saw a striking difference in that about 64% of patients adopted therapy if they were told their sleep apnea was mild, versus between 80 to 90% if it was moderate to severe. And we saw the trends continued with adherence and persistence to therapy. Some of those who were mild, we couldn't get on the phone. So part of it was we couldn't talk to them to be able to go through results. And they are able to get access to the results often before we can get them in follow-up. And the question is there a perception around the diagnosis, right? Does mild mean for some that they underestimate the impact of what it could be? And so getting the diagnosis right can make a big impact on what those outcomes are. And we know, again, the consequences of not treating sleep apnea are profound, irrespective of your severity. It's going to increase your risk for hypertension, cardiovascular disease, metabolic dysregulation, accident risk, depression, motor vehicle risk. I can keep going on and on because it literally impacts everything. And we know the opposite is true, that when you get someone the right diagnosis, you get them on the right treatment, and you get them to stay on treatment, because again, it is a chronic disorder that requires ongoing management. You're able to reduce healthcare utilization and cost and improve quality of life. So truly for us, again, conclusive sleep testing closes those diagnostic care gaps that have emerged with traditional home testing. And so by measuring direct respiratory physiology, Nox AI enables accurate detection and the clinical meaningful severity classification across all patient populations. I will say, I love that Yon and team wanted to keep studying more and more people. They would get the results and they say 1,000 is not enough, 2,000. And I loved it because, again, they wanted to ensure that they were really transparent and making sure every population we saw the same results. And so, what I really want to say is that's kind of the end here. We would love to take questions, but beforehand, I don't want to forget that we want to thank the SRS Foundation for the opportunity to share this talk with you. And we're so thankful. So please, any questions that you have, we would love to take them.
Andy, I see here there's a question if you can make a definition of the adopt, adhere, and persist.
Absolutely. So adoption to therapy is when someone physically says, beyond saying, yes, I want to initiate, and this is just with CPAP therapy, I want to initiate CPAP, but we see them actually using their device. So if someone just says, I want to, and they never use it, we don't count them in that category. And so we kind of we said that we want to make sure it's not just them training, and trying to use it. So we wanted at least an hour of continuous data of using it when they went in that adopt category. Adherence to therapy is us following them a year later, and they are still using their CPAP therapy. And then persistence to therapy is, are they still using their therapy 2 years and beyond? And this data was a 4-year data set. So we wanted to make sure everyone had at least 3 years of data when we looked at them.
Okay. I see we have a question also about how does Nox BodySleep difference between obstructive and central apneas, given that there's no EEG signals. And they also ask about the correlation with the PSD classification. I don't have the number with the agreement right in front of me right now, so I don't want to say a number that is not absolutely correct. But to distinguish between central and obstructive events, we have the ripples. And they measure the absence or presence of respiratory movements. And this is really the key for us to detect the central apneas. We have in the FDA 510(k) summary, which I think the FDA has not published yet, but it will be online soon, in coming days, maybe a few weeks, the numbers. But if you want to reach out to us, we can also share with you the actual numbers. I just don't have them open in front of me right now. We have also another question of we detect COMISA. Did you want to take that one?
So we measure it internally within our programs. We are looking for that as far as we measure ISI in all patients who come in. And that is going to be the next data that we're looking at is does COMISA impact as far as adoption, adherence, persistence, and trends. And we also have, we are lucky that we have digital cognitive behavior therapy. So we have Somrist. It's something that we can offer our patients. So for anyone, we are identifying COMISA at the time of consultation, both based on when they're filling out the ISI and based on symptoms but they're all seeing a board certified sleep physician. So if we are suspecting COMISA, we are recommending CBTI as well as potentially PAP, and it depends often the severity of symptoms and really what the physician's seeing with the patient. They may want to address it depending on the severity of insomnia. They may want to treat that first and then do testing. Or depending if they think the sleep apnea may be impacting it more, if they might start with testing and then reevaluate their insomnia afterwards.
I also see two questions that I maybe want to answer together. So one is asking about a bit more of the details of the models, and the other one is asking if it can be used with devices that are not Nox devices. So the models are convolutional deep neural networks, and they're running in the cloud. So concerns with running on slow machines in hospitals is mitigated that it's just running on the cloud. It's only validated, it's only intended to be used with data from Nox devices. So when we do the validation, we only have data from Nox devices in the validation because data that is from other vendors is not representative of the intended use of the device. And that's why the validation would not give a representative performance numbers if we include data from other vendors. I see also a question about the implication when a patient is more accurately diagnosed, the likelihood for increased adoption adherence. I know you have some insights there.
No, it's a great question. I mean, I think I'm going to take some of this data with a grain of salt, and I will say it was more profound than we expected. Definitely what we want to do is see if there are other characteristics that may impact it. But I will say we did find that historically a lot of the patients, and I think part of the challenge is that they're able to get the results before we can get them back, that when they're able to see their severity is on the milder end, we have a hard time actually getting them. Actually, if we're able to talk to someone, get them back and follow up, that also tends to increase someone adopting therapy. But I do think just anecdotally from clinic that there's different motivations on why someone comes in. So if someone is symptomatic, they may be more likely to adopt therapy if they were essentially sent here, maybe by a partner, by referring physician or someone else, and maybe they were not excited to initiate therapy. That can be a challenge anyway. And if they see that maybe I'm on the milder side, they may underestimate the impact that it can have. And I will tell you in personal practice, I don't ever like using the word mild because it doesn't correlate with severity of disease. And there's been many studies looking at that where, you can have, if you're having a lot of sleep fragmentation, a lot of arousals, you can have a lot of issues with, daytime fatigue, daytime sleepiness, quality of life challenges, and it also can impact, obviously, cardiovascular health and others. And I will tell one quick story, this is one that actually told me to never, ever use the word mild. I had a patient who had documented mild cognitive impairment on neuropsych testing and had MRIs, lumbar puncture, blood work. And at this point, we were his last stop from his neurologist to see if sleep was playing an impact. And his AHI, he had an in-lab study, his AHI was a 5.2. And I believe sleep causes almost everything. So I will say I am biased. But in his case, I said, I just don't think it would do this. I just didn't believe it would have the impact. And he has a PhD, so we were kind of going back and forth. And he was like, there's nothing to lose. And we agreed, and he got on therapy. And I saw him back a month later, and he felt his symptoms had improved dramatically. And we believed it was placebo. We were like, this doesn't make sense, but it doesn't matter. You're still better. And then he got retested 7 months later, and he had a reversal of his mild cognitive impairment. So we had objective measures that showed that by treating his sleep, it made a difference. So again, mild to me definitely doesn't denote severity of disease, but I do think that that's not always the case in how people see that. And I could say that both on the physician end sometimes and on the patient end.
And I see there are a few questions asking about the validation data. So in my presentation, I referred to a paper that we published recently on the Nox BodySleep AI model. So I just encourage you to go and look at that. The FDA will publish our FDA 510K summary in the coming days. That will include a lot of data. So hopefully you can look at this up. And we are also planning to submit scientific papers to publishing. So all of this data will hopefully be available soon. There are questions about pediatric population also. The DeepRESP device is intended for 18 years and older. We have not looked into pediatrics. There's a lot of variability, of course, in pediatrics depending on age. So it's very difficult to make a prediction, but since it's not intended for pediatrics, I think we cannot make any claims on it, and we haven't looked into it. How we deal with artifacts and signals in the AI models, I love this question, and it goes on to say, ask, that the effort data is like signals that's either lost or totally intermittently. We have a publication out on the Nox RIP sensors that they are actually very reliable. So they are typically, if you put them on, they will stay on and the wires are not breaking. So we use single-use belts, so ensuring that the wire is not broken in the belt, it doesn't break from washing or anything like this. And it's one of the signal that tracks breathing very well. The way we deal with artifacts, and this is a real thing in developing the AI models, is that when we're training the models, we also expose them to a lot of artifacts, and we create artifacts artificially in the signals because we want it to be robust against the corrupt or missing signals. Of course, if the input data is not good, then it can't be used to score sleep studies. The outputs of the AI models will also not be reliable. But we do introduce some artifacts when training the models to make them robust up to a degree. As much as, if there's no information in the data, there's nothing we can do. But we try to deal with it like this. And there was also a question if we were using PSC-AHI or RTI. We were using PSC-AHI, so not including the RERAS. The reason we don't include RERAS is that the scoring of RERAS is very, there's a high variability in how and if RERAS are scored. So it's very difficult to train and especially validate models because the data from the sleep clinics is not so reliable on the RERAS scoring. And that's why we have not included RERAS at the moment. There's so many questions that are coming in. We will surely go through all of them and get to answers. We had also a question about quantifying respiratory burden. So the outputs from DeepRESP include the ventilatory burden, hypoxic burden, and the endotypes of sleep apnea. I also see a group of questions asking about when it's going to be available and if it's a separate device. So Heidi and I are fortunately on the scientific and the clinical and AI sides, and so we don't have anything to say about timelines when we launch into markets and things like this. So I just encourage you to follow our communication on the market availability and reach out to your distributors if you have questions about this. What was the other thing? Yeah. We have also questions about, I just have to pick this up because it's also interesting to me. If we think about the uncertainty of the measured AHI value, no, we don't calculate a value of the uncertainty. This is something that we are actively working on though, more for operational purposes to just identify patients that should be looked at very carefully versus those that we are pretty concrete in the outcome. But the uncertainty of the AHI, of course, touches into both the sensors, the variability of AHI within patients. I mean, they will not have the same AHI during REM and non-REM sleep, early in the night or late in the night, or between nights. So this uncertainty of the AHI is a great topic and something that we keep thinking about, but we don't have the answer there yet. And there's a question about pilot collaborations and research-focused partnerships. Absolutely. And I think I just want to end with this, is that for us, validation and transparency is the key. And so we really encourage scientists to either collaborate with us or do research on their own and publish their findings, because of course we want to know that the medical device works, but we also want to know if it doesn't work, because it is something that we would like to learn quickly if there is a problem so we can address it. And so we really encourage people to either reach out to us. We can talk about research collaborations. You can talk to your distributors about this. and they can direct you the right way. And we really encourage scientists and the scientific community to look into this, do the research. We are open to collaborations. So absolutely.
All right. Well, we want to thank so much everyone who joined. We want to thank the SRS Foundation for the opportunity to be able to share all the exciting research with BodySleep 2.0. And the official recording of the webinar will be provided to all attendees and as well on the SRS Foundation website when available. Thank you all.